In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute. Remember, in this universe of wonder and mystery, sometimes the most unlikely heroes make the biggest impact. Keep your mind open, your heart brave, and who knows, you might just find the ether within yourself. So here's to Dayton Miller, the flute.
All right, hello and welcome everyone. See the boys, Shalom and Nominal in the chat. What's up? Shout out to the lads and ladettes. We're gonna go ahead and go live here. All right. Hello and welcome everyone to the Celestial Theodolite update number 5. And we have a quick couple of announcements to make here. I'm going to mute you real quick, Gally. You're hot micing. Quick couple of announcements to make here. So Celestial Theodolite number 4. My attitude was pretty poor. I didn't deal with the conversation very well. I was very dismissive of everyone that was participating, primarily Jesse and John, and I would like to apologize to those two in particular, and also Dazza. I was pretty rude to him and dismissive. But I want to do this in full transparency, right? Because there's nothing to hide here. And I think this is one of the most significant proofs put forward. So obviously anyone participating in the conversation, I'm not just going to bar them from it or whatever if I get annoyed with them. So I'll have to find another way to deal with that. But anyway, I would like to apologize to those three, and moving forward, I'll do better. So a quick recap that I would like to get into for the Celestial Theodolite and the significance of this is the starting with the hypothesis and null hypothesis aspect of the framing of the conversation. And this is extremely important because this is the backbone of what is called, the scientific method, the backbone of academia, the backbone of pharmaceutical drug trials, right? If you want to get your drugs approved, well, you're using a null hypothesis. So if we're going to talk about cosmology and physics and the merger of the two, we should probably do a null hypothesis and hypothesis scenario so we can find the likelihood of how true what we're putting forward is, right? And be as scientific as possible about it. So I'll kind of give a recap on the null hypothesis. If you're not familiar with it, you can think of it like the US justice system, where innocence is assumed, guilt has to be proven through a series of, compounding circumstantial evidence that that makes it so overwhelming that it's like, okay, the likelihood that that person's innocent has been falsified. So the alternative hypothesis that they're guilty is more likely to be true. So I can't tell you what the shape of the Earth is, right? But I can tell you what it likely isn't using some references, which we'll get into. So a long debate that's been going on for the last century is that of optics regarding the spatial field and the visual field, how we see things, how we perceive them, and where they physically exist in three-dimensional reality. For example, I have things on my desk that I could reach for, and the chance that I reach for it and miss because it's deviation from the spatial field and visual field is great, is very low. It's not going to happen, right? Like it's linear at this distance, right? And I have other things in front of me that also give me references. So with that, I can ascertain the correct spatial and visual location for the objects that are close by. But as you get further away, there's a deviation from the spatial field, and the visual field experiences different rates of optical compression. So it goes through a range of hyperbolic, elliptical, and forget the other one at the furthest extreme. But the way that you could plot it out would be a logarithmic scale where you get that nice L curve. So you have linear portions, hyperbolic portions, etc. So that's what best fits it. But the most important part of this is there's not one singular unified model of optics, right? Because the spatial field is Euclidean, that's provable. And how we see it, there's measurable deviations that can be plotted through hyperbolic functions using negative curvature, using constant curvature, assuming spherical curvature, assuming what is it? I can't remember the one that Lumberg had, but the bottom line is all of these experiments that are done, only like one part of a theory can explain, one part of this experiment, and then it gets falsified by another. And this goes on for all the different types of curvature that you can have. So it's all these curvatures at once, kind of, depending on distance and how far something is from you. So it's extremely important to understand that.
We're looking for?
No, it's not parabolic. It's starts with an E, I think. I'll look it up at the end. So we have all heard of the azimuthal grid of vision, the azimuthal dome, your personal dome of vision. What is this deviation from the physical space? Like, how is that manifested? Well, it's manifested in a dome of vision. You see with a radius, right? That's what makes a dome. Domes have radiuses. So you can assume that there's a radius involved. But what's described in astronomical textbooks from the 1920s is we see the dome of the heavens projected above us, but don't be confused and think that that's an actual dome. That's due to Earth curvature. We know that the Earth's a ball, so don't, it's just an illusion. But this is what they're putting forward. We have solar panel manuals saying the exact same thing. The sun is projected as in your azimuthal dome relative to your latitude and time of year. It's going to be projected, at this elevation in your dome. This is how you're going to see it. NASA going on to say the same thing, talking about the moon illusion and how you see it in this projected area here, where the true moon is over here. Right. So this concept, no matter what model you believe in, this description of optics is true. So it doesn't matter if you think we live on a globe or if we live on a flat Earth. This way of perceiving the reality around you, and in particular, the celestial bodies, they're apparent to you in your dome of vision. Now, it's really interesting because we have these celestial bodies in our dome of vision. Now, what can we do with these? Well, however long ago, some lads got together and figured out that they can use the sky to navigate, and they came up with a coordinate system that could be used to represent ground positions of stars with respect to a specific time of year. So they take a snapshot of the sky on the vernal equinox, and they came up with this coordinate system here. And this was verified by taking zenith measurements of stars after they did trigonometry. So basically, they just took the angle and the distance they were traveling to the star, and then they would take a zenith measurement after they traversed the distance. And to complete that triangle, the star was supposed to be directly in the center of their telescope when they looked up, and it never was. So they had to come up with correction angle, or a correction angle, and the deviation from the expected is what they called Earth curves. They called it. They added it up to a value of incentricity. So a deviation from a sphere, like they give it that value of all the corrections that they had to make this coordinate system work, and that's what's known as the reference ellipsoid. That's how they came up with that. And you could read all about that in a book called the Supplement to the Nautical Almanac and Nautical Ephemeris from the 1960s, where people were asking, hey, how did you guys come up with these corrections for the almanac and traverse tables and all these things? And the British Crown put out that supplement to everything. And it was basically a story of, taking zenith measurements to stars, coordinate system transformations, and Long story short, that's the baseline for how they came up with everything. And then we know about what happened with the arc of the parallel when they took follow-up measurements, and where things were off, they corrected due to gravitational potential. So now we have two models to describe this coordinate system, where they say that the ellipsoid is intersecting with the gravitational potential model, and where we get anomalies, that's where we have to tilt our telescope, or we have to tilt our plug bob even further and stuff. So this is where all this comes from. It comes from measurements with respect to the stars, single zenith measurements of stars, right? No manipulating variables, no whatever, right? Just assuming that this triangle should be completed, and because it's not completed, the explanation must be that the Earth isn't flat. It must be an oblate spheroid. It must be this ellipsoid with these dimensions, right? So this is what this coordinate system represents: a position of the stars in the sky on the vernal equinox. And they took this and they mapped it in the north, and then they mapped it in the south. They don't have a God's third eye perspective to see it all at once or anything like that. They constructed this with single, over hundreds of years, establishing observatories, watching transits, all these meridian lines, right? All these represent places where there are references where they of celestial phenomenon, where there's transits of Venus transits, eclipses, of Jupiter's moons, etc. All these things that can be referenced to create this thing. So once they constructed this, now they can project it over different types of projections. So they can do conical, globe, right? They've merged two hemispheres together from observing things from their local azimuthal dome starting in the north with Polaris, right? And then going in the south, and then they merged it all together. So it doesn't matter what you believe in. If you're using this coordinate system, you're using the same thing. And people will say, well, flight route, blah, blah, blah. If you're using latitude and longitude, all of these are the same. That's extremely important to remember. So this way of viewing things in a dome relative to your latitude is not independent of the model. It could go either way, right? So this is what the representation looks like on the globe, on just a different projection, right? So using the latitude, longitude lines, we have the same thing. The sun's being projected in our local dome, same exact thing. So all working on the same concepts. So we have single zenith measurements with respect to the stars telling us that the Earth is an oblate spheroid / geoid, which just means gravitational potential model. All right, so when we look at things with respect to the external reference, we can actually make a meaningful measurement. So this is extremely important, right? Like we shouldn't necessarily dismiss the single zenith measurements, right? Because if you're just looking across the horizon, you're measuring the Earth flat or globular with respect to what? How flat is flat? How globular is globular? Right? So we need an external reference to make the distinction. And that's where the mainstream history used it to construct the narrative that the corrections were due to Earth being a globe with these single zenith measurements. Now, we're going to use this same reference to falsify that claim by introducing another variable, a variable of a mountain peak. But before we get to that, we need to go over a couple of things about the sky so we can understand how we're going to utilize the sky and these things in the sky to make measurements and draw some triangles. So we know that the sky moves at 15 degrees per hour, which comes out to be 15 arc minutes for 4 arc minutes, or for 4 real minutes, which translates to 1 arc minute is 15 real seconds, and then 15 arc seconds is 1 real second, right? And then distance-wise, 69 miles per degree, 1.15 miles per arc second, 101.2 feet per arc second. So this relationship of units of measurement that were derived from this coordinate system, little fractions of the coordinate system, were used so that we could make these calculations and relate the motion of the sky to the ground. we are going to use plane trigonometry at some distance away from a mountain, and we're going to look up its elevation. We're going to look up our elevation and distance from that mountain. We're going to take the difference in our elevation and the distance to that mountain, and we're going to get the tangent of that, and it's going to give us, in this example, it gives us 2 degrees and 31 arc minutes. Now with that, we go into stellarium. We go to the mountain peak, right? We look up in the sky, we turn on the little reticle viewer, and we tilt the degrees to 2 degrees and 31 arc minutes. And we play the night sky out until we see stars that intersect with that time, and we write those stars down and the times that they are at that angle. And then we wait here at our vantage point where we started, where we did our calculation from to get the angle to begin with. And we wait for those stars to intersect with that angle. And if the star is no longer visible when it gets to that angle, that means that it's being occluded by the mountain peak. If it's visible, then that means it's not being occluded and we don't care about it. When we don't see it, that's when we can establish using time, using a timing interval. And for those uncomfortable with timing intervals, remember, people will claim that using time intervals from GPS, you can measure the shape of the Earth. Astronomy is based off of timing intervals. Allegedly, you could use the eclipses of the periodicity of Jupiter's moon's eclipses to determine your longitude. That's a timing interval. So you can use timing intervals for things to establish relationships, angles, etc. This isn't sorry, one second, got to clear my throat. Been feeling a little under the weather, but this isn't some weird mysticism that we're putting forward, right? This is pretty straightforward. So when the star is gone, you can geometrically draw the relationship here that these two intersected, and now it's no longer visible. Now, an important thing to note here is that we are only concerned with the true, quote unquote, true positions of the stars, right? So when you go into stellarium and you turn refraction off, it falls back to the nautical almanac position, right? The so-called true position of the star. And that deviates, by sometimes like 5 to 15 arc minutes. So we're only referencing that true position. We're not accounting for refraction or anything like that. It's when we don't see the star, that's when it's at that angle. And we could look up, we can go to stellarium and we could look up where that star is at that time. And look, it's there. So the geometric relationship established from that implies that this angle and this angle is the same. Now, why is that important? Because if we live on a globe, then when we do this plane trig and we subtract the 8 inches per mile squared for our distance to the mountain peak, the relative elevation for that mountain peak is going to be lower than what the flat Earth predicts, meaning that star will have to get lower in the horizon, which would correspond to a different time, which would correspond to a different angle. Because if we look at this mountain during the day with a theodolite, it's going to measure like 219, right? But if we calculate this out using plane trig, it's 231. So how can we tell the difference in deviation from the visual and spatial fields, right? Is the difference in elevation due to physical Earth curvature, or is it due to optical curvature? Well, using the timing difference of the occlusion of stars, we can actually know the difference. So taking the Pikes Peak to start off with for that example, right? This is what we come out with. This is what the globe predicts. So a literal different time. And what ended up happening was the stars were occluding at that time. And now an interesting thing you can do once you have this relationship is you could actually backwards derive what the elevation is using the angle and the distance in your altitude relative to sea level. So you just add those two together, multiply that by your angle, and that will give you the actual elevation that caused the angle, right? So when you do that, we now have a way to compare what the globe, the official numbers that are purported, we have the official numbers here, and we have the actual elevation that was measured through the timing and the trigonometric function to create that angle. Then we show that the true geometric position of that mountain relative to our position is not 200 feet below where it's expected to be. It's actually 44 feet above where the globe says it is at 4,299 meters. Oh, sorry, I said feet earlier. This is all in meters. My apologies. And so with the difference here at 50.7 kilometers, this is what how much should be missing, and this is how much was recorded. So the globe difference here is way off. And this trend continues at different distances with different mountain peaks. And then, of course, there was the Greenhorn Mountain incident, which we're all anxiously awaiting updates for. Now, we've done some looking into it. We're waiting for Mike, basically. Now, it was put forward recently that perhaps, because there were some anomalies with these measurements, and they don't make any sense, right? They're predicting, or they're showing like an occlusion like 2,000 feet above what it should be, which is that's a bit high. And so what we were looking at earlier is, in particular, Jesse just sent me a screenshot here. What was it? Hang on, why isn't it coming up? Here we go. Copy. Duplicate. Just throw this in here. All right. So it looks like Mike's thing may have been off by 3 degrees because the telephone poles are off by the same amount, and he had to rotate it to get it back into frame or whatever. So the analysis is still ongoing on the greenhorns, but we are working to figure out what the situation is there with that. So that is the update on the Greenhorn so far. Oh, and there's a simulation. So here's the thing. Jesse is doing a presentation on the same subject right now on OmniTalk, which I'm having recorded, and it'll be uploaded on my channel so you can watch for the globularist version of the celestial theodolite update. And then we're going to compare, or we'll get together later during the week or at the next update and address everything in each other's videos or whatever. So that'll be the next celestial theodolite update. But yeah, right now we're just working on figuring out what's going on with these measurements. But the main point of this, right, like the sole core argument of this is that based on the timings, we can backwards derive what the elevation was to cause it, and none of it comports to what the globe predicts. You can't be closer to the globe. You can only be the globe, right? None of these angles show a timing that or none of these timings correspond to an angle that, when you derive what the elevation would have to be, correspond to the globe difference. So, all right. So if the angle here, if alpha is equal to alpha, then the Earth is measuring flat with respect to the stars. That's one of the most important measurements we can have, because it's with respect to an external reference, and it's the only external reference that we have. Because if you're just measuring things on
right.
Earth, then like, it could go either way. And then based on time of day, etc. So let's see. That's it. All right, I think that's it for the Cell Theo update. If anyone has any questions.
Did anyone find the subject not guilty?
Well, real quick,
No?
it basically illustrates like the argument, oh, it's locally flat everywhere, of course. And it's like, oh, there's no mutually exclusive proof for either side, because what they call Earth curve, we call curved visual space. So like, what is the external mutual proof or evidence for one or the other? And this is it. It's amazing.
Well said. And what's so
My
cool
favorite
about it?
part
Oh, go ahead.
is that it works for anyone who can see the top of the mountain peak, and you don't have to put in your actual location into Stellarium. Anywhere you can see the peak because you put in Stellariums, you put in the mountain's location to Stellarium. So that's like, wish I knew what that range was because it seems to be infinite flat.
Almost like they took zenith angles to the stars to create the nautical almanac in the first place using a flat baseline.
Oh, well,
Almost exactly like
that's a
that,
good
yeah.
point. That's a good point, Shane. I wanted to bring that up too. So the Greenhorn Mountain measurement, I think it's like 80 miles away. It comes out to be about, I want to say, what was it, 35 arc minutes of like, that's so low. Like this might be too low of an angle, like, like the threshold or whatever. There might be an issue with that as well.
Yeah.
Like sub 1 degree or sub half a degree might be too low, like the ratio. Because at that level of the horizon, at that far away, like, I don't know.
It's too close to either or.
There well, the optical effects there would we don't know what's happening.
Yeah, I mean it's just too compressed.
Yes, it's too compressed.
Yeah.
But yeah,
Did you say all the Globers were doing the same thing on the other server right now?
Yeah, but it's my fault.
Oh,
wait, what?
But
weren't we supposed to go over there tonight?
No.
Oh,
I mean, I'm not.
oh,
I'm not like a. I'm not. No, that's not what we were supposed to do.
Okay.
We are doing exactly what we were supposed to do.
Oh, okay.
Supposed to be doing. But yeah, anyway, on the Greenhorn measurement, I'll play the video actually, so we can all get up to page on what it looks like here.
You should show the moon one just for shits and giggles too.
Oh, if I can remember which one the moon was. Boom! How did I know? Did I just one tap it? One tap it?
It's so cool.
All right, so this is the Cell Theo.
Yeah, Dyslow, check that out. That's literally what Mike saw, right, through his telescope.
So basically,
see the star right underneath the moon. Yeah.
So basically, yeah, we got this star here. We've identified which one it was because we already went in Stellarium and saw at what time it intersects with this angle, and then all of a sudden we don't see it, and we just write down that time, right? We just look at our phone because our phone is synced to GPS time or what have you, and then we go back into Stellarium and look at the make sure that timing and angle is correct at the mountain peak, and what do you know? It's matches every time.
Every time.
Except for the times it didn't. With the
Greenhorn Mountain.
Yeah. So this is the Greenhorn thing right here. This is about, like I said, 80 miles away at half a degree or at 35 arc minutes above the horizon. And then so what Jesse was showing here, that the telephone lines are tilted, so probably the device was not level. And that's why it's looking messed up.
My telephone poles are always tilted.
Is it? Oh, I don't know then. It seemed more reasonable. It seemed the most reasonable one of his suggestions or trying to make it not align. Yeah. But anyway, this is Greenhorn here. Now, and another thing with Greenhorn last night, the viewing conditions were really bad, and actually we have to. I say we like I did it, but Jesse did a good job. Jesse did a good job of brightening this up so you could see the peak and stuff and outlining it. But yeah, that's the Greenhorn one. So that's the one that's in contention. We have a bunch of other videos of the other ones that correspond to the other data points that were shown on the spreadsheet there. Yeah, here's all the other videos. If you guys want these videos, they're all in my Telegram. So. All right. Any other questions, lads and ladettes?
You kind of grasp the concept now, Dyslow?
Yeah, I mean, I got a lot going on over here at the house, but yeah, I mean, with the tutorial you gave me and all the detailed info, I mean, it's a lot. So I kind of, this is my first time hearing this, so but it's definitely very interesting, and it's kind of like one of those holy crap moments.
That's how we felt when we first heard about it.
What's
Yeah.
the significance with the altitude of the mountain in reference to astronomical refraction? Is there one?
Yes, actually there is. So check this out. When we take Pikes Peak here and we do the prediction for a flat Earth, we enter our, if you guys want this spreadsheet, by the way, you can use this to calculate your own stuff there. And by the way, if anyone has any mountain peaks near them and they want to do some measurements and need help, hit me up and I will see what I can do to help you find some stars at your relative location. But anyway, so we enter the peak altitude, the observer altitude, the distance, right? And it gives us our plane trig angle for 2 degrees, 29. This is a rounding error. It shows 28, but it's 29 degrees and 28 arc minutes. And then we subtract 8 inches per mile squared for the 50.7 kilometers, right? Which takes off 28 arc minutes. So the globe predicts that the actual physical elevation of this is 2 degrees and 14 arc minutes. But if you add a flat 15 arc minute refraction for celestial refraction from the, which is basically what stellarium does, you get a physical elevation angle of 2 degrees and 29 arc minutes. Where does that look familiar at? Oh, the globe exists as a celestial refraction correction to fix the physical elevation angle. And this applies to when we enter other peaks, the missing difference always comes out to be 15 arc minutes of celestial refraction if you add it on. That's why I added this column here, because that relationship's insane.
It's almost like they used atmospheric refraction.
Yeah, because remember we're using
the globe.
Yeah, because remember we're using the quote unquote true geometric position, which is defined by turning refraction off, which gives us the nautical almanac position.
Actual angle. Yeah.
But that's crazy that the missing difference is just a flat 15er off the dome ski. All right. That was a great question.
I have those once in a while.
I nailed it. Nailed it. All right.
Where can you buy celestial theodolite?
Ooh, good question. So
It's your cause.com, I think.
Mike's using something called a C Star, I think it is. It's about $400 or $500 for the recording. He uses that to make the recordings. And it sounds a little pricey, but apparently it's like the best entry level star, like the best thing you could buy for your buck at that level is the C Star thing.
Sell one in like your merch store. I figured like
That's what I was
just get a C. Dude, we're working on a C Star contract right now. Like I can't really say anything further.
What a funny ass name for a telescope company.
And he literally, it's
C-Star.
like, do you want to see some stars? Buy our thing for $400 or $500.
Buy our C Star.
And then you will.
Great.
Yeah.
Any other
So
questions?
what does that mean? That means that stars.
You'll often hear like the Globers say, "Look, we know the elevation of a mountain, and I'm going to go stand at this particular elevation on this other mountain, and look, it matches a globe." But you're saying this is just how they backward engineered the globe.
Curved visual space, essentially. They retroactively took curved visual space and said, "Oh, that's because of Earth curve," rather than the optics of our observations. Long distance observations.
The visual field is Euclidean or whatever you. So all the stars have flat Earth elevation angles in the visual field, but we perceive them in curved visual space. So we get the.
I think you said that a little backwards. The spatial field.
Did I?
They would be Euclidean in the spatial field, and then you would perceive them non-Euclidean in the visual field.
Right. The railroad tracks are actually parallel to each other in reality, right? Euclidean spatial field, and then the non-Euclidean is how it looks like it's converging towards the vanishing point.
In reality, they're Euclidean, right? Like in reality, flat plane elevation angles for everything.
Yep.
Yeah.
That is the geometric
crazy.
relation. That is the geometric relationship insinuated by alpha equaling alpha.
So what does that mean
Extending that
for
triangle, baby. Sorry,
What does that mean for 69 miles per degree, you think? Is that all
Hmm.
contrived, or does that mean that that's based on optics entirely, how we perceive it?
At a specific linear portion, right? For between 30 and 70 degrees.
Yeah, that's what I was thinking. So that means that 69 miles per degree is completely an optical phenomenon.
Huh. Why is it between 30 and 70? Hmm.
Is that the linear portion of your vision extending to the heavens from the horizon? I don't know.
I don't know, man. Shit.
I don't know.
It's almost wait, isn't that the same limitation to the nautical almanac? And then you have like those crazy corrections when you get below those? Or get out of that range, I should say.
Yes.
Oh, okay, cool. Just checking. Seems to be connected.
Yeah, just add a little more celestial. Like that's when the 15 arc minute of celestial refraction isn't enough to make it back to planar.
Exactly.
That's when you got to throw in an 18.
Throwing an 18.
Can you imagine how many physicists had their voices, silenced for voicing and saying what you guys are saying? And so most of us have never heard about all this.
Well,
Right,
you know what?
ton.
You know what they say, Lily.
They say a lot because they're still constantly fighting it out. They're trying to figure out which geometry better fits, the visual field or whatever. That's still in contention, technically. Even have our own example of how we think it'll work better.
Yeah.
Euthymulus torus slice or whatever.
Instead of
The-
addressing the actual observations, let's create another server and go discuss our own version that we like.
Well, to be
What the
fair, I was really rude to them last week, and I wouldn't come back and talk if I acted like that. So I apologize.
You think you caused this?
Yes.
Because you acted rude, they made their own Celestial Theodolite event on the same day that you did yours. Okay.
Specifically.
Right.
Specifically,
Okay.
Yes.
All right. Well, then give him a week or whatever. But I can see that Jesse's showing his same spreadsheet, so I'm sure they're trying to make it about refraction and try to bring in refraction as an actual element, even though
listen, I don't want to spoil next week's Celestial Theodolite show, but we looked at the source code from the simulator. So, we'll see you guys next week. We'll see you guys next week. Not going to do it while they're not here. But obviously, we will reconvene and mend fences, right? Because like I said, in my opinion, this is the most significant proof that we could put forward, because pretty much everyone could do this, even if you don't have the money to actually record it. This is something that you could observe for yourself, so you could know personally. Like obviously your evidence will be anecdotal, but this is something that you could do and verify for yourself if you live near a mountain peak that you could do that at, right? So this is why it's important that we collaborate and address everything as is, because the Celestial Theodolite doesn't need me to get annoyed on its behalf, right? The measurements are the measurements, dude. We're crushing.
Yeah, but if we could listen to other people besides the same three Globers say the same things, that would be nice too.
Well, it's not about us. It's about the new people listening that haven't heard yet and need to know. So that's my bad.
Dicel, do you want any reference material? Do you have the updated that one right there? Do you have that updated spreadsheet? I think I have the old one.
So the most up-to-date
Or the
one is
up-to-date PDF. Yeah.
is the same one.
Just real quick, what you said earlier about timing, astronomy's it's all
It's all
timing. That's
it's
all it
all
is.
yep.
They claim you can actually measure the speed of light using astronomy, which there could be an issue with that, right? Are you on that or what?
Oh man, we got lost so hard in that. That was a 1 second. Here's a link to this dice low. Yeah, I can't even
I'm
remember
waiting for
how
that.
that
The
panned
Andromeda
out.
paradox.
Oh man, I forgot about that one too.
Come on, bro.
Dude, the thing with the Andromeda paradox, it's like the easy debunk of it is like relativity is not even fucking true. Like we can measure, like GPS measures your absolute velocity in any direction. There's, you know, you can use linear interferometry. Like it's like there's no Andromeda paradox.
What about the speed of light thing? No, there's got to be something to that.
Yeah, so we ran into an issue on I forget what the issue was, but we're waiting to figure out something, and I don't think it was ever figured out. I can't remember what it was though. But basically, all we have so far is the reference of the 22 minutes, which isn't the correct timing to give the speed of light. So like what's referenced in Stellarium right now doesn't give agreement with the mainstream, but there may be some other way to calculate it. I can't remember the specifics on it though. Jesse.
Hey, I'm here.
It's all the Globers defendo.
Hola.
Yay, opposition. Oh, and Dr. Mike's here. Dr. Mike.
Hey Jesse, I saw you you measured
Hello.
a telephone pole, dude. That's pretty badass.
I like telephone poles.
Yo, what's up, Dr. Mike? Yeah, anyway, Jesse, before we begin, I wanted to apologize to you for last week. My behavior was pretty rude, and you were just asking questions and I was very dismissive. So I apologize for that.
Well, thank you. That means a lot, Alan.
Cool. So I was telling the lads a little bit of the potential 3-degree deviation with the telephone pole. I thought that made sense or whatever. But then No Tanks brought up that it normally looks that way under level conditions, I guess. So like depending on whatever. So I don't know. Maybe it's not. I think that one made the most sense so far.
Okay, let me drop a picture for you to live stream here, to show on your live stream. It's one I gave you also in Telegram, but I'll drop it here.
Yeah, I was trying to open it from Telegram and my Telegram wasn't popping up. Wasn't opening correctly.
But Jesse, do you have any yet that show the globe result or no? Do you have any ones that are actually showing the globe timing?
There's one that's halfway between, but a little bit closer to the globe timing. But my skies and work schedule have not been cooperative. But I do have a spot picked out that should give a perfect globe match. So if you look at this picture here, Alan, I took a full frame from Dr. Mike's time lapse and overlaid it with Stellarium. But in this case, I rotated Stellarium 3.81 degrees. But you can see there's a strong correlation with the stars there. Even the dim stars were leaving kind of a trail in the time lapse, and you can see that those all correlate to some medium brightness stars in Stellarium. And then, of course, the 3 on the bottom are super bright.
Oh, I see the streaks here. I got you. The streaks are the overlay.
Yeah. So I think I'm quite confident that the camera was rotated 3.81 degrees because rotating it the other way 3.81 degrees not only makes the telephone poles vertical, and by the way, a vertical pole at a great distance does look plumb if it's plumb. So, I mean, you can experiment with that with your camera or something. But anyway, it's not like it was one of those fisheye wide-angle lenses. This is a very, very narrow field camera, so it's not going to be doing that kind of stuff. But anyway, the 3.81 degrees not only made the telephone poles plumb, it also lined up the skyline to both Google Earth and Peak Finder, and it, most importantly, it made gobs and gobs of stars match stellarium perfectly.
Did you say you did this one, Jesse? Was that what you were presenting in there? Like the one? Did you replicate it?
No, this is a still.
Yeah,
From
that's
Dr.
a still
Mike's.
from Dr. Heffron's time lapse. I just overlaid it with stellarium to the same scale.
Had
Yeah.
you tried to do it?
No, I want to, and I got spots picked out, but between work and the lousy weather, I haven't gotten it done yet.
Yeah, the overlay definitely looks pretty close with some of these that you lined up for sure. I agree.
So this whole thing is that the camera is like tilted. That's Jesse's claim, is that that's because it ends up having this tilt to it.
There's very strong evidence of it.
And then how much does that change the result? Is that your claim, that it changes the result? And then how much does it change it?
No, it doesn't change the occlusion time. It just answers the question of why did the ridge line look higher on the right in Dr. Heffron's time lapse when it should have looked a little bit lower. And my answer to that is that the camera was rotated to the right 3.81 degrees.
And that's just for the Greenhorn Mountain you're referencing?
Yes.
Mm-hmm.
That's it? That's the only refutation though, right?
That's the only one that was claimed to not have been in the intended direction.
Gotcha.
Wait, but the
Yeah.
important part is the occlusion time of the star, which is not affected at all by this very slight camera tilt. Is that
correct? And
Correct.
all of these,
Yeah. Right.
But wait, the timing still gives like a time that gives like 2,000 feet too high though, right?
right.
So it's like the issue is still there.
Yeah. But I did you see my Desmos calculator?
Took a Gandy at it.
Yeah, so you can use that, or Dr. Mike can use that, and that'll tell him the exact distance he needs to get in order to get perfect flat Earth results.
When you say perfect flat Earth results, would that be like a distance from like 25 to sub 80 miles?
It depends on the observer height and the mountain height.
So like all the ones that we normally have.
Like the 37 other observations?
Yeah. Let me drop a link to that, and you can bring it up on your screen share, and you can just put in the distances and heights, or the height, the observer and mountain height for a Greenhorn, and then you can slide the distance slider until the red line crosses the top of the higher mountain.
Very nice.
Or if, for those of you who want to get globe results, you just slide the distance slider till it crosses the lower mountain. That's the globe Earth mountain. So basically,
cool. Do you have the link?
Yeah. Oh, hold on.
Excuse me.
So Dr. Mike, do you
in the chat,
do you think your camera was rotated or misangled 3.8 degrees? Possibly.
So I think Jesse's evidence is very compelling, and it probably is rotated 3.8 degrees. Like he says, it doesn't make any difference on the results, but it does explain why the slope is uphill instead of downhill. Jesse does miss the point of this experiment, though. The experiment is not to conform to flat Earth or to conform to globe Earth is to either validate or refute the null hypothesis. And 2,000 feet high still refutes the globe hypothesis because it should be 1,000 feet low, not 2,000 feet high. But at that distance, you have to keep in mind, I think this is the first, this is the second time I've gotten photos from that far away. There's been 2 days this year so far, March 16th and March 23rd. Those were the only 2 days that Greenhorn Mountain was sufficiently clear to get any occlusions at all. And every other day this year, it's been clouded in. And even on that day, when you look at those, at the beginning of those videos, you'll see that it was very, very cloudy. You can see the clouds rolling across the screen until it gets too dark to see. And I guess one of the things we'd have to ask ourselves is it 2,000 feet high because it's being occluded by a cloud and not the mountain?
Right,
And
for that specific video. Right.
Yeah, the nice thing about all the other videos is you can clearly see the mountain. There's no doubt about the mountain, and there's no doubt about whether clouds are present.
Right.
From Greenhorn Mountain, that from 82 miles away, it's impossible to tell. But it was interesting that it was even possible to video Greenhorn Mountain because it should be just barely visible above the curvature of the Earth, and North Peak next to it should be below the peak of the Earth, and yet it's clearly not. So just the fact that the video was even possible is yet another indication the globe Earth model doesn't appear to be correct.
Now, yep.
But in any case,
real quick, can you remind people what the null hypothesis was and restate that statement? So the point of the experiment wasn't to prove flat or globe, it was to prove the null. And what was the null?
Right, and sorry, I'm having a little trouble. This is the first time I've ever used a cell phone and on Discord, and it's I'm still getting used to it. Okay, you'll hear dogs barking, and you might hear a robot vacuum cleaning the floors because the dog's tracking a lot of dirt. But so sorry if there's noise, but
no, you sound good. No background noise. Oh, never mind.
Okay, good. The scientific method says it's impossible to prove that a hypothesis is true. What it does is it relies on refuting the null hypothesis. And the null hypothesis is the exact opposite of the hypothesis, and it's constructed in such a way that it's mutually exclusive. So you can't have a case where both the null hypothesis and the hypothesis are both true or both false. If one's true, the other has to be false, and vice versa. And so the hypothesis I was testing was that the Earth is a globe. The null hypothesis is the Earth is not a globe. And my goal of the experiment was refute that. Refute that the Earth is not a globe, so we know yes, the Earth is a globe. But unfortunately, I can't refute it. Everything is showing is way closer to flat than it is to the globe. So that was the purpose of the experiment.
But couldn't it be phrased just the other way and swap the null hypothesis with the non-null hypothesis or whatever, and say, well, it doesn't match flat, therefore it must be a globe?
So you can do that, and professors will teach you that if you find the exact opposite of what you expect for your hypothesis, if you can't refute your null hypothesis, just switch them. But I think if you switch them and your hypothesis is the Earth is flat, um, you're coming up with much better evidence that the Earth is flat than you are that the Earth is globe. So I'd have to say the null hypothesis achieved its goal, especially with the very first experimental result, where Pike's Peak was flat to within the accuracy of the measurement. Now, several of the other peaks I've tried, they're not quite that close, but they're still extremely close to flat and not close to globe. Some of them are dead on, some are off by like 50 meters. And I haven't done any testing to see how accurate is this method I'm using. Like if you're sometimes in the videos, it's hard to because of the extremely long time exposure and the star trails that Jesse noted. Sometimes it's really hard to pinpoint when was that star actually occluded versus the time lapse of the star trail being occluded. So that's going to introduce an error, and that introduces an error that would make the measurement appear lower than it is. Despite all of the efforts to eliminate refraction, we all know there's a little bit of real refraction present. It's just negligible for the accuracy we're trying to achieve to differentiate between flat Earth and globe Earth. So that could make things appear a little high. Now, on both of the Green Mountain photos, you can clearly see clouds present at the beginning of the video before it got too dark to see them. And clouds would create more refraction, and that could be the whole explanation for why the measurement is high. But in any case, it's extremely obvious. It's nowhere near what it needed to be for a globe Earth. It tends to favor the flat Earth hypothesis. And there's probably a moral in this, which is we probably shouldn't try to analyze videos that are too dark to make anything out. And we should stick to the ones like some of the earlier videos where it's really easy to see the mountain, it's easy to see the star, it's easy to see if there's clouds.
Real quick, Dr. Mike. So, Jesse, do you agree with Dr. Mike's assessment so far and what he stated about the other measurements being more close to flat than globe?
No. Blodgett Peak is between flat and globe, but closer to globe.
Okay, that's one peak. What about the rest?
Was that the peak that you and Piezo went over?
Yes, that is the peak.
Okay, yeah. So that was the one where the angle was probably wrong or whatever, because if you switch it, the two columns flop. We talked about that earlier, but so we'll have to touch back on that.
Yeah,
but,
well, we did our math from the ground up using just the raw data, not relying on anything else in the spreadsheet, just the timing and the star. And I did want to respond to the suggestion that clouds were making all those stars appear to set 2,000 feet too high. Because I traced out the mountain skyline when it was visible at dusk and superimposed that on the video, we can see that is the terminator line. That is where all the stars, throughout the whole video, they all occlude at that line. So there were no clouds. It was the same mountain profile that was occluding the stars the whole time. And you mentioned, Mike, also that you expected the peak on the right to be lower. If you rotate the video 3.81 degrees so that the star patterns match stellarium, then it is lower on the right. And now that we have the formula to predict the celestial theodolite angle based on observer height, mountain height, and distance, it seems very reasonable that we will be able to get as many perfect globe results as we want by just adjusting the distance, by changing the distance of the observer. Because I tested the simulator on all of, let's see here. I did it on, let's see, Pikes Peak, Blodgett Peak, Cheyenne, Mount Rosa, Blue Mountain, Green Mountain, and Greenhorn Mountain, and it matched all of them. So I think it does accurately predict what will be found, and it predicts lots of situations where we will get perfect globe results. So how would that affect the null hypothesis if we are getting more globe results?
I haven't had a chance to look at your simulator, and all I know is what other people have told me. I got a couple of equations I briefly looked at, and the equations I looked at look like they're adding refraction in, and so I'm skeptical that the simulator can do what you claim. And there again, you're missing the point that the object of the experiment is not to find a distance where it agrees with flat Earth or globe Earth. It's from whatever distance is actually observed from, does it refute the null hypothesis? That's the scientific method. That you have to always realize that hypothesis can't be proved. Therefore, it's necessary to refute the null hypothesis, and being able to predict what the null hypothesis will show does not refute it. In fact, if anything, that validates that it couldn't be refuted because you can predict what it is. So the experiment does not take refraction into account. It's pure, how far away are you? Okay, now that you know how far away you are, multiply that by the tangent of the elevation of the star when the peak occludes it. And that gives you the rise above the observer. Now add in the observer altitude and you've got what we would predict the altitude of the peak is. And then my spreadsheet just looks at the difference in the measured altitude of the peak versus the official altitude of the peak. And in all cases, and somebody's going to have to bring me up to speed on the alleged discrepancy on Blodgett Peak, because this is the first I've heard of that. But on my spreadsheet, even on Blodgett Peak, the measurement was much closer to flat Earth than it was to globe Earth. So I don't think the simulator is a valid thing because it, by your own admission, the simulator predicts the angle found for the null hypothesis, which means it's failing to refute the null hypothesis, which means the hypothesis is presumed wrong.
No.
And so the Earth is not a globe.
No, it doesn't predict the flat Earth results. It predicts the actual angles that you got in each of those different situations, including the Blodgett Peak one and the Cheyenne one that were about equidistant between flat and globe.
Okay, so if it predicts those, it's predicting elevations that are more in agreement with flat Earth than with globe. So it's still not refuting the null hypothesis that the Earth is not a globe. It's validating that null hypothesis that the Earth is not a globe because the numbers are what you would expect from a globe Earth.
No, it's predicting observable reality. So it says that if you got 16 miles away from Blodgett Peak at the same observer height that you were, that you would get a perfect globe match, for example. And so my question is, when people start
Blodgett Peak
this,
wasn't.
When people start using this,
Blodgett,
go ahead.
I was just going to say, Blodgett Peak is not 16 miles away.
No, but you could drive closer to it. And
right, but so now you're speculating. You're speculating. You're not using the actual measurements anymore. So you still have not. You failed to refute the null hypothesis, and that's the problem. The whole goal of hypothesis testing is you have to be able to refute the null hypothesis, and you can come up with a simulator and contrived measurements and say, well, if I was half the distance away, this would work, but we have no evidence that that's true. So we have to go by the actual measurements taken, and do those measurements refute the null hypothesis? And the answer is no, they do not.
Okay, but now that we know how to easily use the method to get globe results, when those globe results come, when people actually go out to the locations needed to get the globe results using this method, how will that affect your hypothesis?
So there again, it sounds like you're trying to contrive a scenario where what you want to believe will agree with the way you're trying to make it happen. And that's not how the scientific method works. The scientific method is you have a hypothesis. In this case, the hypothesis is that the Earth is a globe, and therefore the land should curve away. And when we measure mountain peaks, they should be a certain number of meters lower than a flat Earth would predict they are. And all of the experiments I did are not picking and choosing a location that makes things work. It was taking the peak where it was, taking the observer where it was, not driving to some special location. The first few measurements from my sunroom and the rest was from my front yard, since not all the peaks are visible from my sunroom. And all of those measurements fail to refute the null hypothesis that the Earth is not a globe. The measurements show that the Earth doesn't appear to be a globe just from those measurements taken where they happen to be. So what I hear you arguing is if you fudge the data, if you find the ideal location and the ideal peak, you can come up with something that agrees with your expectation, but that is not the scientific method, cherry picking data. You just have to take the data as it appears.
I had a question on that. Is that how science works? You could falsify something, like you could falsify something, then somebody else could do science and then unfalsify your falsification.
That's not the way a null hypothesis works. A null hypothesis is the one thing that cannot be true for the hypothesis to be correct. And because you can't prove that a hypothesis is correct, what you have to do is refute the opposite of that hypothesis. So the scientific method is refute the null hypothesis, and then you from doing that, you can quantify your level of confidence that the hypothesis is correct. In this case, in all these measurements, our confidence that the hypothesis is correct is extremely low.
I know, but I'm just.
Oh, go ahead.
I'm just saying, somebody could come along and falsify your falsification? They could unfalsify it?
Well, they would have to come up with basically they'd have to use the null hypothesis as a hypothesis, and then they would have to falsify what was the original hypothesis. So I think you can see the problem that to falsify if the hypothesis is that the Earth is flat, what you have to do to falsify that hypothesis is the null hypothesis has to be the Earth is not flat. And when you set about to falsify that null hypothesis, that's when you discover to your amazement and horror that the evidence seems to show that the Earth is flat.
So
yeah, but they would have to have data that shows the opposite is the key too. You'd have to actually have.
They don't have any data, right, Gio? They still
Yeah.
haven't presented any of their own occlusion timings that counteract our observations or our timings.
But that's sort of what Jeremy is almost getting at, is that, yeah, if something's been falsified, if something has been falsified with data, could you then try to falsify that falsification? But in order to even do that, you'd have to have data that shows something
Your
different.
own observations, right?
Yeah, and repeatable actual measurements and data that would show something to the contrary.
Yeah, but I'm saying
Yeah,
that, like, once you falsify. Sorry, real quick. Once you falsified something, how could, like, unless your methodology was wrong, how could you unfalsify your falsification?
By
How could Jesse come along and undo what you did unless your methodology was flawed or something?
right, by invalidating
So-
the
so-
methodology.
Yep, and so that's a good point. Once you falsified it, and so you can't unfalsify it. But what you can do is you can swap the null hypothesis with the hypothesis. So instead of starting with the hypothesis that the Earth is a globe, you could start with the hypothesis the Earth is flat, and then in that case, the null hypothesis would be that the Earth is not flat, but it does take an entirely different set of data to falsify that null hypothesis. And what this entire experiment inadvertently discovered is that the data is showing that the Earth is flat. So it's going to be a hard hypothesis to falsify.
Well, I have a question. If I can drive to a certain point and then follow the method and get globe results, does that invalidate the method?
And the answer is no. It's cherry picking data. If you're driving to a particular point that falsifies it, probably a good example is my doctoral dissertation, stochastic analysis of progress tracking metrics. To falsify my hypothesis, what I had to do is simulate 3,000 years worth of software projects using stochastic data that modeled real world collected data and show that null hypothesis was false for 90, I think the standard they held me to was 95%. So I had to show it was false for 95% of those simulations. And nowadays, people are doing things with models and simulations. I personally prefer the old scientific method where you have to go out and do real experiments, not simulations, because it's too easy to make mistakes on simulations. It's a lot harder to fudge real world data.
Right, but here's the thing, though. The Globers have been telling us for years you can't prove things using science, which I could debate everyone on that thinks that. But so you're saying we can't 100% falsify things now either? Because if somebody can
Well,
come
no.
along and unfalsify you, like, now what? You
Okay,
can't
so
falsify
like what
things.
he's saying is that for Jesse's thing, he would have to say that like 95% of the data like matches the globe. But what Dr. Mike is saying is that wouldn't be the case. If you're going to a particular location to take the data, then you wouldn't have 95% of the data match it unless you're like cherry picking, which would mean that you'd only go to these places to test it.
Yeah, like let me go
Dr.
to a
Mike
place
didn't
within
go to
2
a
miles.
place to test it. He just went where he had it, you know. He wasn't going to achieve certain results. He was just where he was at, took multiple different measurements. But like, you know, to do it the other way around, you would have to, yeah, say like that 95% data matches this, and you're not just like picking, you know, one particular location. I think that's what they were saying.
So
But
The close.
you can't 100% you can't 100% falsify things in science either. Then is that what we're?
So on Ether Roundtable 63, I did a presentation called "It's Debatable," where I went over how to go about falsifying the null hypothesis, and it's all about level of confidence. So you can never prove a hypothesis to a level of confidence, but you can refute a null hypothesis to a level of confidence. Most doctoral dissertations require that level of confidence to be somewhere between 95 and 99%. In the case of that presentation, I falsified the null hypothesis to 6 sigma. So it was 0.999999999% certain that the null hypothesis was refuted. But you're never entirely certain you've refuted it. The scientific method is a search for truth, so there's always uncertainty involved. And when you dig deep enough, you always find anomalies, and new knowledge lies in those anomalies. So one of the things we should be doing is explore all the anomalies. Sorry, I'll be quiet and listen.
Well, I actually had a question for you. What would be the reasoning as to why you can't prove things? I sound like a little kid. Why can't we prove something 100%?
But we're
using the
getting
scientific
hella
method?
off.
What's the reasoning?
We're getting hella off topic.
Can I ask a question?
Yes.
All right.
So what if I just happened to be in the right location to get a perfect globe match using the method? Would that be different than if I had intentionally driven to the location that gave me the perfect globe match?
Yeah, if you could show different distances at that same globular location, like Mike did, that would be like, oh, okay, cool, it's ambiguous or whatever.
I mean,
that'll do it.
I mean, if I'm following the method to the T, does it matter why I am where I am? I mean,
Yeah, it matters how far away.
So yeah, I've heard you say something several times that tips me off to the piece you're missing. For you, apparently, distance matters. With the method I used, distance did not matter. I observed peaks at various distances from a relatively fixed location. For all practical purposes, it was from the same spot. So it was various distances, and each of those distances refuted the null hypothesis. And that was using peaks that were just where they were. I had no control over them. So I didn't happen to luck out on all those peaks. Those peaks were where they were, the distance they were, and I had no control over any of that. That's what you have to do with the scientific method. You have to take the data the way it appears.
Yeah, you weren't a flat earther before these observations. You just wanted to help Taylor out with her theodolite observations and etc. And you came to your own conclusions, and we heard you out, and we're like, holy shit, this is a great concept, the celestial theodolite. Taking the timing of when a star gets occluded by a mountain peak, therefore you can remove the refraction argument between the observer and the mountain peak and actually get the true geometrical location of the star using stellarium. And it's like, you didn't expect it to match, but it matched. And then to confirm it, you did other peaks and other stars at different times. What has the globe shown?
Yep, and I'd only add that I don't think Taylor needed my help. In fact, I'd say she was more of an inspiration. That she inspired me to get off my butt and use the scientific method to try to determine is the Earth flat or is it a globe? And to my surprise, it was flat.
Impressive. Thank you, Dr. Michael.
So if I have a spot picked out that should give me globe results. It's 24.73 miles from a mountain that's 2,337 feet high. If I go to that spot and follow the method to a T and it matches the globe, does that invalidate the method?
The first sentence out of your mouth invalidated your method, because you're saying, if I go to a spot where I expect to get the results I'm looking for, is my method invalid? Well, yes, it is. If you're going to a spot that you're certain is going to prove your hypothesis, you're doing it all wrong. The whole purpose of stochastic analysis for my own dissertation was everything was random. I had no control over what was happening in the simulation, all I could do is let the simulation run, collect the data, and after the fact, analyze the data where it lay, to see if it was within 95% refutation of the null hypothesis. And luckily it was, and they approved my dissertation and I got my doctorate.
Well, so what if I just happen to be at that same park just for fun? Maybe I take my sweetie out there or something and it gets dusk and I time an occlusion from that same location, but because I was already there for other reasons and then I get globe results, then does that invalidate the method?
Yep, your location's tainted. You have to take your sweetie to a new location completely randomized.
Yeah, I mean, I guess in a way,
Yeah,
like when Jeremy brought up the like falsifying a falsification, this is in a way, Jesse, this is what you're trying to suggest, is that if you go out and get globe results, does it then? Now you keep saying it invalidates his method. Do you mean it invalidates his data or his conclusion or the actual method? Because if you're following the method and saying the method gave you globe results, then obviously you would have to say the method is valid if you're trying to say it's a globe. But the point he mentioned as well is that if you're going out, seeking a certain result, then that's already a different intention to begin with.
Well, the point I'm making is
It's a rigmarole.
If the distance has such an effect on it, such that it allows the results of the method, when correctly followed, to match flat or globe, then wouldn't that invalidate the method as a way to determine flat or globe, if it could give either just depending on the distance?
I disagree with your contention, because if you look at Mount Rosa, for example, it's a different distance, and it equally shows from my observation location that it's a flat Earth result, not a globe Earth result. And all of those peaks were far enough away that there's a clear distinction. It's easy to tell the difference between a measurement that supports globe Earth and a measurement that supports flat Earth. And that's what you're looking for. So if you just happen to drive out to some location and you just happen to take a measurement, and your measurement says, oh, well, I can refute the null hypothesis the Earth is flat. Now what you want to do is what I did and look at other peaks and see, are they all refuting that the Earth is flat? Or was that one just a fluke? Because that Blodgett peak was the second one I did. And that's when I realized when you get too close to the peak, there's not enough difference to have a high level of confidence that you're seeing the difference. Like you said, it's pretty close to, it could go either way on that particular peak because I'm just too close to the peak. So you want to choose your peaks, you want to choose your distance such that there's a clear distinction between flat or globe.
Well, so that it does sound like you're agreeing that based on the distance and the height and the elevation relationship, you could get flat or globe. So there's something missing.
No, I'm not really saying that.
Well,
so you might want to spin it that way, but that's not at all what I'm saying. What I'm saying is, yes, if you get too close, you can't distinguish between them. That's not refuting the method. That's missing the point of the method, which is to be able to clearly distinguish.
Exactly. So if you get closer, or like how Daza was saying, like, oh, why don't I use a peak that's only a mile away? Well, because the difference between flat and globe is so minute, you can't tell which one is true or not. That's why the distance has to be exemplified, right? The longer the distance, the more different between the flat prediction and the globe prediction. Because if you're on a globe, then the mountain peak would be tilting away from you and be lower. Thus, the timing would be different. So you guys still have to show those timing occlusions that match the globe. And the only way you can do that is if you do the same exact way, the method, right? Accentuating the distance between you and the mountain peak. It has to be enough distance to basically show a huge difference in arc seconds.
You mean arc minutes?
Arc
I mean arc
minutes.
minutes. Sorry. But yes.
So you'd agree that a broad random sample of points would be better than a sample from one fixed location, right? That we get a better understanding.
Yeah, bring it on.
It's the
We're waiting
well,
for you.
it's
the
not
other
just
scenario that's
the
going
it's
to
not just the
overwhelmingly cover all
location,
of the
it's the
points, right, is the
distances.
setting of a star on the horizon.
Oh, do you hear Daza, Alan?
Yeah, I do.
Yeah.
I was trying to answer his question. My
I think it's
bad.
like 7 or 8 mountains, right?
Yeah, we have different
How many-
distances already.
Yeah, don't we have like 7 mountains?
Yeah,
All
we
at different
have
distances.
30
Lodge Peak,
something-
Cheyenne, Mount Rosa, Blue Mountain, Green Mountain, Greenhorn Mountain. How many is that?
7.
Yeah, but you need to do some from sea level, different atmospheric
What?
conditions, because we know that impacts refraction, right?
Is it?
Dr. Heffron, I was gonna ask you, did you ever confirm the location of the stars if they're saying like this is not the location of it because it's being refracted, so like stellarium's wrong, but have you ever tried to get the angle of the star with your what's it called, your sextant? Just like confirm that it's actually there if they're saying it's being refracted.
So I haven't. I've only heard that argument with respect to Green Mountain, and with Green Mountain, because it's so far away, it's so dark. It's hard to positively identify any of the stars except for the way Jesse did it. I think Jesse, where he overlaid stellarium in the actual video, that's an excellent way to confirm the identity of the stars. But I have not tried to do that, and the reason I haven't tried to do that, the whole premise of the celestial theodolite is there is nothing more accurate than where the nautical almanac says the star is. So I don't need to confirm it. I just need to know what time the peak occluded it, and I do know where the peak is.
So
Distance and angle equals height, yeah?
I think as to the azimuth of the peak, we can pretty much conclude that if we know the occlusion time, we can get the azimuth of that occlusion point from stellarium, right?
I agree.
And then we can go into Peak Finder or Google
Up
Earth.
the mountain, not from his location.
And then we can go into Peak Finder or Google Earth and then see where that azimuth lies, and if it lands right on Greenhorn Mountain, then yeah, it's probably Greenhorn Mountain. If we know the star and we know the occlusion time, we can get the azimuth angle, and if we've got the azimuth angle, we can tell the mountain it clipped behind.
I think that doesn't work because, once again, you're going to predict a different angle to the mountain than we do. Because the mountain should be at a certain angle, and then you add refraction or whatever. So you're going to have to like try to use refraction to make up the difference between the predicted versus actual. But that's why we transform to the location of the mountain peak to get the angle to the star. We don't tell stellarium where we are. I don't think stellarium's going to be able to tell you where the mountain's going to be. Only the star.
So this is my proposed site. It's 24.7 miles. The mountain's 24.7 miles away. And the difference between globe and flat is about a little over 10 arc minutes. So that should be usable, right? That equates to like over 400 feet, right?
Yeah.
Okay, cool.
10 degree arc minute difference between flat and globe? That's kind of hard. That's not really, not too, it should be a bigger difference.
No, that's plenty big. 10 seconds.
10 arc minutes is
10 arc
big.
minutes is going to be like, what is that going to be, like 20 seconds, 30 seconds, something like that?
Something like that, right? It's 4 seconds per arc minute,
Yeah.
right?
No, that's significant.
Okay. All right.
Yeah. And I'm going to try to have my cameras synchronized to atomic time from WWV on 10 or 15 megahertz as well.
Respect.
Okay. All right, cool. I look forward to it. At least you're bringing something from the globe
trying.
side.
So Jesse,
So,
you're claiming
real
that'll be
quick,
that'll be a raw measurement then? You're not going to add any calculations in order to get your result. It's just going to be straight observed. Is that what you're claiming, or is there
Well,
going to be a post processing?
well, the first step is simply record the exact occlusion time of a star, of a known star at a known location, and then I'll just upload that as a video, and then you guys can apply the Heffron method and see what you get.
got it.
Fantastic.
And the simulator, which matches all of Dr. Heffron's other CT angles, says that this one is going to match a globe, so it'll be interesting.
Wait, you mean the one where you plugged in celestial refraction?
Yes, sir. Hey, it predicted every single other one of his except the March, the earlier March one for Greenhorn, which had misidentified stars.
And you say it predicted, but it seems more like there's a bunch of arbitrary coefficients in here in these various lines of formula that you plugged in.
Well, most of the math is simply astronomical refraction, which is kind of convoluted.
Yeah, well, where did these arbitrary coefficient numbers come from? It looks almost like you plugged in all of his observations in an Excel spreadsheet and did a form-fit plot curve and took the formula and plugged that into Desmos.
Oh, no, let me get it for you. The astronomical refraction stuff all came from a PDF that Shoebill gave me, and I will copy that page to you. Hold on.
Because I think we have, if we go back to one of those first versions of Dr. Mike's Cell Theo Pres Allen, remember that chart he had with the celestial refraction formula on it?
Yeah, from GG Bennett that gives 15 arc minutes or whatever for like a uniform correction.
Yeah, can you pull that up real quick? Because I want to compare that formula to the one on this Desmos thing. Because I
can, buddy.
could have sworn the coefficients are different.
I tagged you, Aether Boy, with the formula that we used for astronomical
My
refraction.
dude said Ether Boy.
Ether
What are
Boy.
you talking about, dog?
Used to be Ether Piezo, right? Piezo? Ether?
Do you mean Crystal Wizard?
I don't know.
Address him by his title.
Yeah, it's this one. Keep going down. Oh, right there.
Yep.
Yeah, that is not what they have. So here, right here, let me pull it up real quick. We've got, yeah, completely 34.133 plus 4.197 times the predicted angle, and yeah, we've got some here. I'll show you. Let me just put it in chat. Follow up with what Jesse just posted.
Yeah, we just transcribed the formula from this this page out of some book. I don't even know where it's from, but Shoebill gave it to me because I asked him how to calculate astronomical refraction, and he gave that to me, and so that's what we put in there. Nothing was.
I see.
Nothing was fudged or fitted
Smart's
to
formula.
any data.
Smart's formula. And what is h squared in Smart's formula?
I don't know. I just used it, and it matched Stellarium reasonably close, and so we went with it. We tried to use Stellarium's code from their astronomical refraction correction, but it's like got multiple parts in it, like interpolates between them, and eventually we gave up trying to code that into Desmos and just used the formula from the old paper that Shoebill gave us.
Oh, hold on real quick. Well, you say you don't know what H2 is in this formula. You used it without knowing what it is?
I figured it out months ago when I was converting it to Perl, and then I kind of forgot what it all meant. And then Pink Floyd helped me, and he just recently used this to put it into he helped me with the Desmos.
Right, so I'm looking here, and it's saying H2 is measured in degrees. This is, okay. This is them applying a correction to the like standard angle, right? But this is using a globular baseline, right? So
No.
the smart was trying to calculate refraction on a flat Earth.
No, just refraction. The apparent displacement due to the atmosphere.
Right, but that's presuming what model?
Just it doesn't. It's just a formula that closely
right.
approximates what they. Anyway, it's
But what,
close. It's close to what's in Stellarium. Take it or leave it. The fact is, we took a boilerplate formula for astronomical
you can't just
refraction.
walk away from the question like that, dude. It has to have there's a model underlying the math that's being used here, right? Because the prediction would be totally different. I just find it very odd that you would apply a celestial refraction formula to a mountain and it would make up the difference.
We're applying it to the star.
Well, you're applying it to the star, but it's crossing it at the point of the mountain peak. Isn't that the same thing as applying it to the mountain?
Nope.
If they coincide with one another at a point in space?
Yes, it's
Well,
the same.
look, where the formula came from, we didn't curve fit match anything. It's just
Yo,
refraction.
real quick, Jesse, I have a question for you. Sorry.
Huh?
Are you moving the star up to the observer at the location rather than at the peak?
I'm not really doing anything. I simply came up with a formula that models the method that Dr. Heffron describes, which allows it to predict, based on observer height, and mountain distance, what angle the Heffron angle will be. It's just like going in and doing it in Stellarium, but you don't have to actually go out and do it because it predicts it. It's a simulator.
So can you tell me which color mountain is for the glob and which one's for the FE?
Yeah, the higher one is the flat Earth mountain and the lower one is the globe mountain.
So the purple is the
globe.
Okay. Wait, what?
Well, okay, let me look. I don't have that open right now.
Oh, I'll pull it up.
I don't know. The higher one's the flat Earth, but let me look.
I got you.
So many
I think the
windows
purple's
up.
higher.
Yeah, the purple one is the flat Earth one. The green one's the globe Earth one.
Okay. And then I'm also looking in here, and you have this apparent angle equals FE prediction angle minus D times 22.2 over 36. So where'd you get that 22.2 from?
That's just the arc seconds per mile that something drops in the distance on a 7/6R globe. It just calculates the apparent angle to the mountain. The fact
On
is,
a 7/6R globe.
Yeah. So in other words, at any point, if you are looking at an object that's at a distance that should be, say, the same height as you, the angle to that will drop at 22.2 arc seconds per mile. For whatever
Wait a
reason,
second.
that's just the way it is.
You said 7/6R. You're talking about standard refraction. But the apparent angle right here is for the star.
No, that's for the mountain.
X apparent angle. You're saying that's for the mountain.
Yeah, that's the apparent angle to the mountain, which happens to be also the apparent angle to the star at the time of occlusion.
Okay. Astrorefraction equals astrorefraction raw, which is the formula you plugged in from there, times adjustment for atmospheric refraction. Why are there two?
Well, look in the page from the PDF that I pasted. You see there's that second part, probably the yellow part. I don't remember. It's been months since I actually converted that to Perl scripting, and then it was P. Floyd who just recently did it into Desmos. From this same page.
And you have Heffron equals apparent angle minus astral refraction plus D over 69.0468. Where'd that number come from?
Well, D is just distance in miles, and then that's 69 degrees per mile. Or 1 degree per 69 miles.
1 degree per
Yeah, per 60 nautical miles.
Okay. And you're saying that if I adjust these sliders, what will happen?
You can change the Heffron angle by changing the sliders, and you can also change the mountain height and the observer height by changing the sliders, and you can find the combination you want that creates, or for a given observer and mountain height, you can find the distance required to make it match either flat or globe.
This K mountain width is just arbitrary, just to make the mountain wider for preference, right?
Yeah, this is for fun. Because like if you're
And this T is what? What is this T?
Temperature in centigrade.
Okay.
Because that affects that's one of the inputs to the astronomical refraction. So that affects the red line a little bit, not much.
How would
I don't
the
see.
mountain refracted, like block if they're both refracted, like, you know, I could understand maybe the star for this case, but the mountain too?
I don't see any combination of observations where this red line crosses the green mountain.
Can you stream what
and
you're
not the
showing,
purple
Piazza?
one.
Can you stream what you're
Yeah, hold on.
showing? Thank you, sir.
Hold on. Yeah, 1 second.
So if you put in the heights, put in everything for Blodgett Peak, and set the distance to 16 miles, and then it'll cross the globe Earth mountain.
Blodgett, hold on. Set the distance to 16 miles.
And this is also in feet and miles, not meters. Sorry, but I can get those for you.
Blodgett Peak.
So you're moving it closer to match the globe.
Right, exactly.
Why?
To make it indistinguishable to try and corrupt the method. So this is the inverse of what John did. So whereas John went to the extreme at 1 mile, Jesse's going slightly longer, right? But you wouldn't.
So
But
if
same thing, yeah.
If you notice, right? So here's the thing. If this angle for celestial refraction is correct, or this formula rather, if this is correct, right? Like this is accurately modeling the behavior. This should be precise, plus or minus like 1%, right? I mean, at this point in modern science, then this red line should be comporting with that green thing all the time, not the purple thing. This green mountain is the glob, and this purple one's the FE, right?
Well, if the method was unambiguous, if it worked regardless of distance, then yes, but it doesn't. You can.
Well, you're plugging in refraction in order to say it doesn't fit with the FE prediction, right? I mean, like.
Yeah, we're doing ours with the raw geometric position of it and just the planar trigonometry. So what you're trying to do doesn't seem quite the same.
Regardless of whether you understand or agree with the validity of the math, the system works. It accurately matches every single one of Dr. Heffron's tests so far, except the two first ones for Greenhorn Mountain, which had misidentified stars.
Hold on, wait. This formula right here, you just told me this is the apparent angle to the star, right?
Well, to the mountain, and it's the same as the star because it's at the moment of occlusion.
Well, hold on. It can't be the same as the star because this line's not crossing this mountain right here. So is this apparent angle for the mountain or the star?
Neither. That's the Heffron angle. That's the result. That's the altitude angle, the unrefracted altitude angle that stellarium gives you in the final step of the Heffron method.
No, this is X. This is the Heffron angle right here, X Heffron. This right here is apparent angle. Hold on. I'll tell you what. If I just change a number, I can see what changes. Yeah, it's definitely to the star. See how that line to the star changed? Okay, so you have the apparent angle to the star being the FE predicted angle minus a 7/6R Earth correction. So you're applying that position to the star in this model that has both mountains. You would need to have two different lines. You need to have this apparent angle be the one for the glob prediction, and then have a separate line that doesn't incorporate refraction for the other one.
Yeah. Well, that's the beauty of Desmos. It's free. You can take and make a copy of this and modify it however you like. And at the end of the day, though, my version matches all of Dr. Heffron's data points, valid data points. So, I mean, you can modify it if you want, but you can't make it any better. All you could do is make it so it didn't match all of his data points. But so far, it matches all of his data points, and it was not fit to his data. It was made from other independent sources just based on the geometry of it.
But wouldn't you
What
get
is
the curve? Like if you're using the 7/6R, which assumes the curve of the Earth, wouldn't that be already assuming a shape? How would you be then testing the shape?
So the reason it does that is because it needs to know the apparent angle to the mountain, and that just happens to be, even if Earth is flat, for whatever reason, that is the formula that gives you the apparent angle to a mountain. And so I'm just using that because it gives the apparent angle, the accurate apparent angle to the mountain.
But is the mountain apparent angle assuming curvature or not?
Wow.
Well, it should be in the paper that he linked, right? Like that's the question I asked him. He's like, it doesn't matter, it just does work. And I was like, no, bro, like it matters because there's an underlying assumption. Because if you were to say that works on a flat baseline, it would be there would be a different distance or a different height delta across distance, any distance.
Yeah, it fits the refraction curve or whatever.
But also
up
one
to
of my
15
biggest problems, I
degrees.
haven't had a chance to like analyze this or anything. But
Yeah, take
just
your
at
time.
first glance,
Hit me up anytime.
at first glance, I can already see that the apparent angle to the star, you just left one apparent angle, and you said that the apparent angle to the star is whatever the FE prediction is, and then you added some correction for refraction.
Well, look at the Heffron angle calculation, just a couple lines up. Yeah, there.
Heffron,
yeah.
okay.
See, it has
Apparent angle. So you have. Oh, sorry. So hold on. This is not how we do the Heffron angle either, because you said it's the apparent angle, which includes the FE prediction minus terrestrial refraction, minus the astronomical refraction angle. Dude, Michael Heffron does not use refraction at all. How are you going to call this a Heffron angle and you put two different refraction coefficients in there?
Because it matches the results of his method when carried out.
Bro.
What?
This is not his method. This is not his method, bro.
It's but the
Simulate
formula,
it how it's not, and then I can prove it wrong, right?
but the formula matches the results of his method.
Oh my
That's
God.
my
Oh my
only
God.
goal.
I'm not going to sit here on stream and plug in
I'm
every
done.
value off his spreadsheet. I can tell it's not his method by what I just said.
Well, I
Are you
plugged
being
in
deceptive again, Jesse? Is that what's going on?
No, I personally plugged in a value for Pikes Peak, and let me just read them all off here. Pikes Peak, Blodgett Peak, Cheyenne, Mount Rosa, Blue Mountain, Green Mountain, and Greenhorn Mountain. And every one of them, it correctly matched. So I'm telling you it works. If you find one that doesn't work on it, then we'll look at it. But so far, all the ones I checked worked. I think even if...
Well, that's mathematically retarded, though, so...
Hold on a second. Wait. You're saying, let me get this straight. You're saying that by you taking what he did, right, and what he did was literally just use plain trig with refraction turned off. You're saying you took that same data and you plugged it into a formula that uses two different types of refraction and got the same result, and it matches both ways.
Do you realize that the red line represents the altitude, the unrefracted altitude angle given by stellarium in the last step of the Heffron method?
This line? No, you just said this 22.2 is the amount of drop over distance on a glob with a 7/6R. You have plugged in the glob into this line.
Okay, scroll up just a little bit. Oh, there it is. See where it says right there? It says X Heffron equals, and then it's like 0.727747. Do you see that?
Yeah.
Okay. Do you recognize that, or are you aware that that is the angle, that the star altitude angle unrefracted, that's given by the Heffron method from stellarium?
So wait, you're saying that this right here this output is in degrees?
That is in degrees, yep. So if you set the observer height and the mountain height and the distance to any of Dr. Heffron's valid data points, which is most of them, then that Heffron angle will be very close to the angle given by stellarium.
I see. Give me 1 second.
Okay.
I have a question. How would a refracted mountain even block a star? So why would we put in, like, the refraction of the mountain in there?
Good question. Why is refraction in this formula?
Because that's
Twice.
what it took. That's what it took to make it match.
To match a globe.
Well, no, to make it match all of Dr. Heffron's results.
But it wouldn't match. It wouldn't matter anyway, because if the mountain was refracted, then you would not have it block a star.
Shouldn't block the star. That's the reason we turn refraction off. That's the whole point.
And is it including all variables? That formula?
Well, I mean, I think that there's some assumptions being made here about like curvature, right, Jesse? Aren't we assuming like a globe in this formula?
I'm not assuming anything. I simply use the formula that matches Dr. Heffron's results with using his method.
But you gotta do a bottom up, not top down, thing to like explain it, because you can't just say, oh, this matches it, and that's like, yeah. I mean, because like the mountain, that's the point. It's like the mountain's actually there. So what would happen if you turned off refraction for the mountain? Because that's what he's kind of shown with this, is like the mountain's actually there and it's not being refracted or, anything funny. It's like in its like, the elevation that it would be predicted to be, without curvature, none of that. And also like the 7/6R, I would argue, wouldn't even be like valid for, the nighttime, based on like, the calculations with the temperature gradients, because we showed that they even out at night either way, but that's another topic. But either way, like a fracted mountain couldn't occlude anything. So I think that we should just turn that part off.
But the globe needs it. You can't do that, Taylor. If they do that, then it's over. So let's keep playing around in make-believe land with two types of refraction on our representation and just say that it works.
Why can't a refracted light wave be obstructed by the mountain? I'm confused by
He's
that.
saying the mountain's also refracted.
Yeah.
So
the path of the light, the overall path of the light is refracted, right? Follows a particular path. If the mountain happens to be in that path, it will be occluded.
So you're saying that this matches his observations, bro? Because right here,
it's feet. You got to do feet.
I'm doing it in feet. This is 2,075 feet and 2,870 feet. Well, like, what is this?
Okay, hold on. Let me. Which peak is this?
This is Blodgett Peak.
Okay, so the Blodgett Peak observer elevation in feet is 6,808. You got it in meters.
Okay, 1 second. Gotcha.
Okay, so so anything that's refracted cannot block or obstruct other light. Anybody can just look this up. It's very easy to see, because it's like saying like a hologram or something. It's not real. That's just apparent, right? So it's not going to block or obstruct other light.
It's not the refracted mountain that's blocking the light. It's the mountain is blocking the refracted light.
Okay, well, that's the problem. Jesse put refraction for the mountain as well.
That's
Into
just
the
to see the
sun.
angle that the mountain is at. In real
No, the
life.
mountain's not at a refracted angle because a refracted mountain doesn't block a star. That's the point.
And the
So he
mountain
added it back in at both points, right? At the star and at the mountain, just like we knew they needed to make it work.
Yeah,
upside
but we're
down.
not measuring any physical angles here, right? It's just occlusions.
Oh, it's just a
But
timing interval like GPS and all of astronomy. Yes. Yep.
should be
Exactly.
9429 or whatever. Okay. There.
Hello.
See? It's right between them, a little bit closer to globe, which is exactly what you get when you do the Heffron method on that data. On that
So
occlusion time.
Heffron
I
is
joined
not
the server and I don't.
Now,
I'm
if you
sorry.
try dragging distance.
Hold on
to
1 second.
something-
If I take his average altitude using hold on 1 second.
His average altitude was derived from his method, right? So don't get too circular.
Wasn't he trying to disprove flat Earth? So wouldn't the calculations assume flat Earth instead of like globe?
Yeah, you can't.
Dude, it assumes the actual geometric position of the star too. It's like this whole like moving the star at different locations, adding your adjusted thing that's close to stellarium. Like, is it at where stellarium's at or not? Like, what?
Yeah, so here's the problem.
Go ahead.
Here's the problem, right? What I can do to check the veracity of this is I can plug in what the height was shown to be through the timing. Now, you could say that's not the actual height of the mountain. That's fine, but it's the occlusion point of the mountain, of the star with the mountain. So what should happen is if I plug in any particular height that uses his timing of the occlusion, this line should always clip the top of this mountain. It's not doing that. And this difference is because of the refraction you put in there.
No,
You're
I
not
disagree.
using his method.
I disagree.
This is not his method, bro.
Well, why
You said
not-
it matched everything on the sheet, and it doesn't.
Well,
This should
you
be
just-
clipping his mountain.
You just put in. You didn't put in the in order to get the accurate results, you have to put in accurate data. You put in you put in an elevation for the mountain, which is different than the published elevation. You put in the one that he derived using his method.
But
right?
yes,
You can't
yes,
test
and that
his
should
meth-
be.
You can't test his method against his method. Of course, his method matches his
But-
method.
I'm not
But
testing
wait.
his method against his method. I'm testing to see that this star is occluded by this mountain peak with your simulator at his time.
My simulator assumes correct mountain heights put in. So
Okay, either way, I put both in. Neither one of them had this red line clipping this mountain peak.
well, that's because his results didn't. For Blodgett Peak, remember we went over this map.
What do you mean they didn't, bro? The star got occluded at a particular time.
Do you remember a few weeks ago when we all went over the math and we all agreed, including you guys, that the Blodgett Peak one was slightly closer to globe? Remember that?
There was a particular star, I think it was like HD 216 718 or something like that.
Right. And by the way, I did all of them and averaged them, and the average is also closer to globe. One is it's 4.77
The average.
arc minutes from globe and 4.92 arc minutes from flat. Yeah, most of those are closer to globe. I think one was closer to flat.
Maybe you can show it getting clipped by putting in his data or whatever, just to clear up Piezo's point. And then I want to get back to the refracted mountain.
Well, Piezo, the big point here is, does the simulator, when given actual mountain heights, accurately match what the Heffron method gives? And the answer is yes. If you were to put the actual mountain height, the published mountain height, in the mountain height field, you would see that it gives the same or very close to the same angle as using the Heffron method.
At 1 second.
Saying if you add in refraction at both ends, you can make it match the globe every time. That's really impressive.
That's pretty
just
much
what-
all we're getting from
How
this.
that would be logical. You can only add in the refraction of the star or something because
Nope.
you know,
You could do it
refraction
both
cannot
ends.
block refracted light cannot block other refracted light. That's the issue. Just like
Now,
if you saw
91.55.
it's not exact, but it's close.
9156. All right, so this shows it clipping at 9156. All right, let me go to the spreadsheet.
Oh, also, try dragging the distance to 16 miles and see what he would have got if he happened to live 16 miles from it.
Why?
Well, because Piezo had said that, expressed some doubt that there was any combination of distance that would have matched globe, and I'm saying that 16 miles in this case will.
Actually, bro, it has you. So I just checked it. This point that it clips at, this line clips this mountain at, is 9156, right? 9156 feet. I just converted that to meters, and I got 2,791 meters. The official altitude is 2,870. So that is about 79 meters below the official altitude of the mountain using your formula. This angle to the star with this is your spreadsheet. This angle to the star, bam,
I'm not sure what you're
9156.
Well, no, you got to go to the center, not at the edge there. Go to the center. Yeah, there you go.
$92.08.
Right, which doesn't match flat or globe. It's equal. It's halfway between, closer to the globe slightly.
2,806 meters.
Remember, my claim is that the Heffron method is not accurate. Depending on the circumstance, depending on the distances and the heights.
Well,
it
your
can
method
match-
shows the star getting occluded at 2,806 meters, which is still 64 meters below the actual official mountain height.
No, this is not showing star occlusion angle. The red line represents the altitude angle, the unrefracted altitude angle of stellarium when set at the mountain peak at that time.
This is not the unrefracted angle, bro. I just showed you there's refraction in it. Both the apparent angle, which is this is the angle to the star. I just proved it by changing a number and it threw the line off, right?
But
right. So
it still matches the results very closely using the Heffron method. So you tell me why I had to
What
put
the
refraction
none of
to
the
match
numbers,
Heffron method.
bro. I just plugged this in. Right? I got 9209 ends up being 2,807 meters. Okay, 2,807 meters. If I go to the spreadsheet, you got 2,807. The official is 2,870. Mike's average was 2,829, and the globe was 2,933.
So does the Heffron angle given by my simulator match the angle that Heffron obtained in real life for this particular?
Does your simulator match the angle Heffron obtained? No, the angle he obtained was at 2829. That's what I was saying. The angle he obtained, if you follow my mouse, right, this is, hold on, 2829, convert that to, 1 second, to feet, 9281 and a half. So the angle that his predicted was right here. Right here is where this is. See where my mouse is? Right there. That is where his spreadsheet shows that his occlusions happened. So the line that you're tracing is not matching the line of where his occlusions happened.
Okay, do this for me. Let's look at HD 116.718 since that's the one we looked at before. And the red line the Heffron angle should be 1.84444 degrees. So 1.1844. So adjust something to make the Heffron angle equal to 1.184444. Or just set it to, or just go in there, Heffron angle, and just replace the formula with.
Hold on, why are you trying to jump to a different point, bro? Before we go to that, can you explain to me why this right here, 9281, 9281 would be right here. where my mouse is.
I can explain because you don't understand how this is working or what's
No, bro.
going on.
Bro, you just asked me if it matches what he got, and I'm telling you. So what he got, you're saying if this matches what he got, then this line that you painted should be the line that matches what he got, right? That's
Yeah.
what would what else would be a match?
He got 1.1844 degrees. Right? Am I right? What angle did he get for HD 216 718?
HD 216 718.
Yeah, what angle did he get?
1.196.
Okay.
It looks like your formula says 1.168 right here.
Okay, well, for some reason, the 1.196 is not what you and I and everybody got when we all went over it together. But go ahead and put that red line at 1.196. Is it at 1.19? Yeah, okay, there you go.
Yeah. And it shows 9267, and it should be 9281.
So, the angle that he got, which is a little bit inaccurate because it's not what we all came up with when we went over it super careful. But anyway, the point is,
What?
it's still, that is the angle of that line, and it's still not matching the peak of that flat earth mountain. It's significantly below it. And when we all went over it with super careful, we got even a lower number than that. Oh, the mountain elevation that we all used when we all went over it was 9429, not 90 whatever you got. I don't know if that's
So
94.
maybe I should use a different mountain for this purpose.
What's that?
One second, Taylor. In the middle of getting to the bottom of something, will take a minute.
No, this is 2870. This is the official mountain height I'm using right here. 2870 meters is 9416 feet. Yeah, but so what I did find just now is that if I plug in the 1.196 that he got on the spreadsheet, at 1.196, he got 2824.9 meters. 24.9, which is 9268 feet. If I go here, it says 9268 feet. So it looks like this line is crossing 9268 feet correctly.
Yep.
Excuse me.
Yeah, like I said,
At that point,
red line predicts what that angle is going to be that using his method is going to give. And try dragging the distance over to about 16 miles.
Why 16?
Oh, you got the because that's where I think it would match the globe. Because earlier you had said you didn't think there was any combination that would match the globe, and I'm saying 16 would. But you might have to change that fudge factor you put in.
Oh, I was doing that to make it, match up. So let me get this straight. What you're telling me, right, is we have here, let's pretend Dr. Mike's method, right? Let's pretend we didn't make any conclusions about the baseline that we're on. We just know that we go out and we measure it, and we take some stars, and we find out what time they disappear. All we know a priori is that stars only get occluded by physical objects, not uplifted mirages of them. And then we take this data and we plot it. You're telling me that in your worldview, we have these very precise coefficients for astronomical refraction, terrestrial refraction. All this stuff is supposed to be a very precise science. I mean, look, dude, we've got to the 5th decimal point paired with second order squared angles. And if we do that, you don't think that it should just match the globe all the time? Because this right here is where the mountain is. How could the star be getting occluded so far above the mountain?
My contention is that the method itself is invalid. I don't posit it as a proof of globe or a proof of flat because I'm showing that it is not consistent. It can give either.
See, I'm pretty sure that when we went through all of these observations, right, the only ones in which there was even like remotely close between the FE and glob numbers was Blodgett Peak, and everything else was like drastically different. And like you're hanging on Blodgett Peak, but we're also calling into contention. Dr. Mike is calling into contention like that might not even be the actual altitude of the mountain. Because if it is the actual altitude of the mountain, how is the star being occluded by a mountain that's below it?
Blodgett Peak and Cheyenne were about equidistant between globe and flat. Rosa was spot on for flat. Blue Mountain was between them, but about 1/3 from flat and 2/3 from globe. And then, of course, a Greenhorn Mountain was 2,000 feet above flat Earth.
I'm looking right now at the list. Blodgett Peak averaged -40 for FE and +60 for glob. That's the closest one you have. Cheyenne's -49 flat and +93 glob, +3 flat and +182 glob for Mount Rosa, -30 flat, +163 glob for Blue Mountain, +17 flat, +216 glob for Green Mountain. And so I'm just wondering, right, like we're way closer with FE on everything except for this one mountain, right? What if it's just that these mountains that are said to be, over 3,000 meters high, what if their actual altitude is just a little bit different than their published altitude? Like, do you think it's crazy to think that the actual mountain could be 17 meters different than what they publish?
Nope.
Because otherwise, how is the globe off by 216 meters when FE's like spot on? Or 182 meters when FE's spot on?
Well, Greenhorn Mountain was 2,000 feet off, and that would be noticed because a lot of small planes would be crashing into it because those pilots are like, okay, there's a mountain ahead, it's a certain height, I'll be 1,000 feet above it. Well, if it's 2,000 feet tall, bang, in they go. So, no.
Yeah, we have to figure out what's going on with Greenhorn Mountain. We already had a conversation about that. I don't think it's off by 2,000 feet. I don't think anyone's arguing that as far as the altitude of the mountain being off by 2,000 feet. But the point being, right, is if it's a glob and your refraction calculations accurately model the glob, then they should accurately model the occlusion timing. Right, because his whole position is a null hypothesis. What are we falsifying here?
Well, that's my question. When we
What?
start going out at the correct distance to get perfect globe matches, then what will we be falsifying?
Shouldn't every distance be a perfect globe match? Because we have refraction accounted for. That's y'all's whole paradigm, is once you account for refraction, everything matches the glob.
Well, no, I mean, let's say,
No?
Here, do this for me. Put in an observer height of 19 feet.
What distance are you about to make this?
The distance will be 24.74 miles.
Do we have any star occlusion timing data to go with this?
Yes, it's predicted. I haven't gotten out there yet because the weather's been bad and I've been busy with work. But I want to show you what I'm planning to do, and I can give you GPS coordinates and everything. It's all public locations.
Okay.
All right, and observer height. Okay, you got 19 feet for observer height. Okay, oh, you haven't. Okay, there you go. And 2337 feet for the mountain height. The temperature slider's handy, isn't it?
So you're predicting that you should measure this at this distance. Is that what you're saying?
That's what the simulator predicts using the exact same math that it matches every single other one of Dr. Heffron's valid data points.
Okay. So real quick, if we then just change any variable, why does it not match glob anymore?
Because it's not a valid method for doing either. It can be
No. That's the point here. When you plugged in, see, here's what you did. You derived using a different set of math, right? You didn't use the math he used. You used refraction, which is supposed to correct for optical effects, right? So once you have corrected for optical effects, we should be able to figure out where the occlusion is going to happen. Now, it could make sense, right? It could make sense for the occlusion to happen at a lower point below the mountain peak, because the star could be technically be lifted up if refraction was really like going crazy over here and doing all this stuff. But it would never make sense for the star to be occluded above a mountain peak. And that's
Unless there
the
was
other
cloud.
problem, right? Because
Thank you.
this right here would be saying that, okay, let's say that we do have refraction, right? And that because of refraction, right, the apparent image of the star is getting lifted up, so it's getting occluded a little bit later than the actual mountain peak would show, because it's being lifted. That's plausible. But it would never be plausible to say it's getting occluded by a mountain that's below it. That just doesn't make any sense. This is physically where the mountain is on a globe. This mountain right here cannot occlude this star ever. So what you've done, actually, in my opinion, Jesse, if you've done anything, and once again, it's to be determined, right? This is my first time looking at any of this. But if you've done anything of useful validity here, you've shown how refraction can account for an extra X many seconds added to the occlusion timing, because the star is being lifted up higher than its true position, so that it occludes a little bit later compared to the true mountain peak position for a flat Earth. But for a globe Earth, it still should not even be occluded yet, period. So in my opinion, you've actually just done more work to damage your model here. Because how's this mountain that's underneath this light stream occluding the star?
Oh,
It's not.
well,
It's not.
Right, and that's my contention, is that the method itself is not consistent with reality.
I think it's that the glob is not consistent with reality there, buddy. You're almost there. You've almost gotten it. You're so close. This we know the star got occluded. These are real world measurements that we have, bro. The star got occluded. It's a fact. But how could it be occluded if this is where the mountain really is? It couldn't be. So the fact that it did get occluded means that this is not where the mountain is. The mountain has to be up here. And the fact that it's got occluded below the mountain peak is because refraction lifted it up and added some extra time to the visible light in the sky.
Well, remember that Heffron angle is not the angle of occlusion. because you move stellarium, forward to the mountain, and that causes the star angle to rise 1 degree per 60 nautical miles, right? Right? We do agree that if you get 60 nautical miles closer to a star, it appears 1 degree higher, right?
Did we just hold on?
Dude.
Did we just come? Go ahead, Alan.
We just came full circle, dog. What the ruck?
Well, it's a question.
Bro,
You don't have to answer.
No, bro. What are you talking about? The lad is here on the ground at 0. He calculated 2 different predictions, and as Piazio just pointed out, the timing isn't globular.
Well,
Like what did you just say, dude? You just said that moving it to where, dog? It was observed not being there from the distance away that it was derived from. What are we talking about?
He keeps equating the red line with the angle of occlusion as seen from the observer, but that's not what it is, and that's not what it's supposed to be. The point is, whether you like the math or not, whether you understand the math or not, so far, this simulator matches every single one of Dr. Heffron's valid data points, and it also lets us see where we need to go to get globe results. And so my question is, if I go, like I said, 24 miles from this mountain and get a star occlusion timing and it matches the globe, have I invalidated anything, or have I just brought refraction into the equation? Refraction that just happens to make it match a globe.
It's
Well,
impossible though.
let me ask you a question, Jesse. If you're using a wrench on a bolt that's too small to grip because it's like a big wrench, right? You conclude that the wrench is not a valid tool?
Well, no, but I think we agreed that 24 miles and 10 arc minutes was not too small to tell the difference between them, right?
Mm-hmm.
Okay.
Let me ask a question. Is the 4/3
So
R?
So
Is
Jesse,
that required for your timings? Do you have to add mountain refraction to get your timings to match?
yes.
I just use the Heffron method as published.
This is not the published Heffron method, by the way. Like I need you just I just need you to acknowledge that first of all. Like whatever you think you're doing, whether it's valid or not, this is not the Heffron method.
Heffron had nothing to do with the creation of the simulator. But
okay, so you said that this was the Heffron method.
Oh yeah, you repeated. Hold on a second, Jesse. You repeatedly call that the Heffron method, the Heffron angle, right? So like,
but it's not.
It's not though.
But
so no, it's not.
But it matches the angle that he got on all of his valid data.
Bro, it's not, dude.
It's
you have refraction incorporated. That's not the method.
We literally just went through it, and it doesn't show that at all, man. Yo, I'm gonna go ahead and wrap up for the night while we're all still cordial.
Well, thank you, Alan. I do appreciate the effort.
Yeah, no worries, man. And again, apologize for being so just abruptly rude on last Tuesday. It's uncalled for. But yeah, I think today we've reached our maximum ability to conclude and communicate effectively here. So why don't we call it a wrap here and reconvene next week?
Can I just real quick, Alan? How you doing? And I really appreciate the disclosure you just made. I think it's really big of you to admit that publicly. So big up on you for doing that. And hope the lads are doing well. I see all the lads are here. I'm just curious if you guys would be up for formally doing more measurements of this type, and then from what we find, creating an actual p-value. Because I like, I gotta say, I like that you're looking into the null and alternative hypothesis. It's a good start. I'm just curious if there's been, because on the basis of a single measurement as scientists and statisticians, we generally don't conclude against it, or we don't generally make a conclusion one way or another as to reject the null.
So we have 37 measurements from different distances, or that incorporate 7 different distances, and we also have 2 locations that people have done their own, and those distances and stuff are not published. They don't, because
Cool.
it's at their house as well. But yeah, I agree. P values are tight and stuff. We should definitely P value it up for sure.
So do you think it would be appropriate of me if that happens to say that it's not a real P value? Just asking.
It's appropriate.
Would you be angry if I said that to you? Would you be
Mord
angry
one,
about that?
Mord one, I don't think I could ever be angry at you.
Well, it's just that Piezo is here, and Piezo slandered me. Piezo slandered me personally and professionally.
Morty,
by saying my
this isn't really
So
the
I'm
place
just
to hash
curious
out
if,
that. Keep it to.
Well, no, it is. It's a public forum, and I was slandered publicly. I'd like.
Morty, what are you doing, bro? All right, lads and ladettes, we're going to wrap up for the evening. Big shout outs to Glenda and Tony Coriolis for helping to support Ether Cosmology and our endeavors. Thank you guys so much. The support has been awesome. You guys crushed it. We're so excited to get everything out to everyone. It's going to be awesome. And just a quick reminder, the whole store ends on Tuesday. And then we'll fill out everyone's orders. And then whatever we have left over from what we have to order in bulk or whatever before we send out, whatever's left over, we'll put back on the store. You guys can order out. But the hoodies will be gone after Tuesday. Shirts and hats may reappear at varying quantities and sizes that are left over. But thank you guys so much for the support. You guys crushed it. I look forward to continue to deliver the stuff for you guys and to just continue to grow. And we are going to build this community and build an interferometer. All right, we'll see you guys. Let's see. Tomorrow we have Shane coming up with meteorites. Where do they come from? Who are they? What do they do? If you haven't seen Shane's first meteorite presentation or meteor presentation, go to my channel or his and search keyword meteor, and it will be one of the Ether Cosmology prezzies. So definitely check that out. And then tomorrow he'll be presenting a new and refined version with some additional information on meteors. Then Wednesday, I think we're taking a break. And then Thursday, we're having a good old fashioned Sagnac fight on the OmniTalk server. So stay tuned for that. Friday night will, of course, be Friday Community Twitter night. And then Saturday, we have an extra special debate on Aries failure with, what's his name? Can't think of that guy's name. Oh, Astronomy Live. I'll be debating with Astronomy Live on Aries failure. That'll be hosted on the Reds Rhetoric channel, but I'll also be restreaming it here. So I'll see you guys for the debate watch party. The boys will be watching it on Discord as well. So stay tuned for that.